This is Official Nerd Business. Hello nerd boys and girls, welcome to our Monday math class. Today we're looking at Euler Problem 5 and how to solve it using Python. Now this Euler Problem 5 is easily one of my most favorite problems I've seen yet, and I'm in the 60s. So yeah, let's jump into it. I've already created our base file, consisting of the description with all the usual parameters in there, and a run function, and our entry point if we run this file on its own instead of inside of the program. The program we expanded in the previous episode to run timing information for us. And let's look at the description. The title is smallest multiple, and if you look at the description, it gives us the number 2520 is the smallest number that can be divided by each of the numbers from 1 through 10. So if we divide this by 10, we get a whole result. If we divide this by 9, by 8 and by 7, etc., I think that's a pretty amazing property. What is the smallest positive number that is evenly divisible by all numbers from 1 through 20? So the description is pretty clear, and the only parameter we need here is the number, the upper bound on the range from 1 to n, on what numbers we want to use, where our target number should be divisible by. Description is pretty clear. You immediately think, alright, if we start out with any number, just add 1 and check if we can divide 1 through 10 or 1 through 20 or 1 or whatever upper bound we set, and then return the first number of which this holds. So I've created one naive implementation of this. Here's attempt number 1. Takes this parameter, so say it's 10. It takes a parameter, it starts I of at 9, and while true, this a while loop will continue to do whatever it does as long as its argument is true, and you can't get truer than this. So this in fact is an infinite loop, and in this case it's an infinite loop from which you can only break out using this particular break statement. And what does this loop do? It increments I, so we set it up to be n is 10, so let's say that we set it up to 9 here and then immediately add 1 back to it. Now it's 10. We say that 10 is evenly divisible by the numbers 1 through 10, and we're gonna test if this hypothesis is false. So for each number in the range from 1 to 10, remember that the range usually gives you a range from 0 to n minus 1, so we need to explicitly say to start at 1, and we need to explicitly add 1 to our last parameter so that we get all the numbers from 1 through 10. And if the current increment modulo the number in range is not 0, so if it does not divide without leaving a remainder, then this number is not the number we're looking for. We need to break the for loop, and this break, so if for instance we get the number 11 on the second loop, and we have a 2 here, 11 modulo 2 is 1, so here we break out of this loop that tests divisibility early, and then we get back to this bit which increments 1, looks at 12 and starts testing again, then looks at 13, and eventually for n is 10 we will hit this number in about 1/1000th of a second. A bit faster in fact. So that's pretty quick. What happens if we plug in 20? Well, it takes a little while longer. I've already ran this naive first brute force attempt, and we get the correct answer. I can spoil this for you. If you type in this over at projecteuler.net, you will get a green check mark, and it took us over 2 minutes to find it. 128.2 seconds. That is a lot. This, once again, is one of these puzzles where you think, yes, brute force approach is quite simple, but we can improve on this. We can improve a lot on this. So let's set up a second attempt. Let's name it attempt number 2. And let's drop the brute force part. We're going to be clever about this. There's a couple of things that we can alter in our original approach. And in fact, we're going to look at let's set this starting parameter. We know in the problem statement that if we look at 10 and if this is the first number that's evenly divisible from 1 through 10. It also happens to be divisible by 20, which is important a little bit later on. And you can see that for yourself quite easily. This number is divisible by 2. Therefore, this number is divisible by 20. Alright, well true, there's nothing wrong with that bit. Oh wait, this. Our number needs to be divisible by 20, so we can only look at steps of 20, at numbers in the multiplication table of 20, so we can increment whatever this is by 20 continuously. We want to test if this first number is, so we have the number given in the problem statement minus 20, and then we add 20 and check for divisibility. And maybe it would be faster to check for divisibility in the reversed order, because the number is more likely not to be divisible by our upper bound than it is by 2 or 3. So this would quit early. In fact, if we drop the parameter and just say, if we do this for a second, this is to solve the actual problem statement. We can later look at generalizing it. But we don't need this particular range. We only need to check if a number is divisible by 20, by 19, by 18, 17, 16. We don't need to check for 16 because 16 itself is divisible by 4 and 20 is already divisible by 4. And it's divisible by 8. We don't have any other parameters yet that are divisible by 8. Okay, let's keep 16 then. 15 though. 15 is divisible itself by 3 and by 5. 20 is divisible by 5 and 18 is divisible by 3. So 15 doesn't really add much here. 14 does because we do not check for divisibility by 7 as yet. Then 13 because it's prime. There are no numbers lower on the list that give us a factor that indicates that 13, or higher on the list, excuse me, that 13 is not necessary to test for. 12 again is divisible by 6, for which we have 18, 3 for which we have 18, 4 for which we have 16, and 20 itself. So 12 is not really interesting to test. 11, and there are no more numbers with factors that matter. So if a number is divisible by these items, it is also divisible by the items from 1 through 20 which we skipped on this list. And we're checking them in reversed order. So this should be a lot quicker. Is there anything else right off the bat that we can do to ease our pain here a bit? I think this is... Let's see if this runs quicker in anyway. So let's, instead of running attempt 1, let's run attempt 2, which doesn't take a parameter. Now run does take a parameter, but it's ignored further on, so that's fine for now. And let's see what happens if we run main. We want to run problem number 5, and we want to look at the 20. This was a lot quicker. So 2.5 seconds gives us the same answer as more than 2 minutes did just a moment ago. But there is a way in which we can do this even better, and that's gonna take some work, because we're gonna look at a problem number 3. And that has to do with prime factors. Turns out that divisibility and prime factors are very closely related. So we're gonna set up a little module that copies our if we look at Euler number 3, here's a function that gives us prime factors of a number, and that's partly based on a function that gets us the prime numbers up to a given limit. So what we're going to do now is set up a general piece of library, a module that has these functions that cooperate with each other nicely, that check if our primes array is already initialized and if it's big enough, and that gives us the prime factors of a given number. So let's create our module. I want to do this in the same directory as all our solutions currently are. Right click on this folder, new file, lib Euler. This is our library with the tools to solve our Euler problems. .py blank file. Let's see, we wanted to copy some code out of Euler 3, namely this sieve. We want in our general library to be able to find prime numbers. That would seem to be a very useful application of this, and it gives us this prime list, which I guess is fine. What do we want to? Let's create a module variable called primes. Let's start it as a blank list. This underscore is added to show that if we import this module on other places, that this is a private variable. Now, unfortunately, Python doesn't really do private as such, so it will still show, for instance, if we go here and import it. Import solutions.liborder as, let's give it the name E. If we then say E dot whatever, we can still access this variable, but the underscore shows us that we should not be doing this. As with a lot of things in Python, there's convention which needs to be followed, and this is one of them. So if you see this, don't directly use this, let the module use this, and then use the other functions in the module to get your results. In fact, this should be private as well. Yes, and then this should empty the primes list and refill it, and it shouldn't return it because it's setting a global. Now we do get a warning here: shadows name primes from outer scope. Now it shouldn't shadow this because now there are two separate variables, and whatever we do in this function will not affect this. But we need to tell Python that it is okay to use the outer variable, and it will usually not do this out of itself. So if we add the global statement here, we show the Python compiler that this variable is indeed referencing our module variable, and we would very much like to change that, please. So here we have the sieve filling our primes, but as said before, this is now basically private. So let's add some modules that are some functions that have some outside functionality, and the one I'm currently interested in is this prime factors function. So if we copy that, paste it in here, then we will see a couple of errors. First of which is that we don't have the math library, so that's easily fixed. That's that. Then it can't find this sieve here. Now it can. And then we also have the fact that this now sets a variable prime, so we wanted to use the global variable primes, which again it now shadows. So let's add this particular statement to this function as well. It now knows to use the general primes function. It doesn't know this anymore, so let's add that. And there is one more thing I want to change in this function. For Euler problem number 3, it was fine to just call this on the blank primes list, but now the primes list might already be filled, and it might be enough to cover this limit. So if the limit isn't too big, if whatever prime value is currently the highest, if the highest prime is bigger than the limit or is less than the limit, we want to run the sieve. And if it's equal to or larger than the limit, then we don't want to run the sieve, because whatever we're going to do in the next bit of code, the primes for this are already on the list. So let's see if our module works. And to do that, I want to skip to here, change the run method a little bit. We don't want to return all of this. We want to create a list, and let's see, n, yeah, sure, plus 1. What does this button do? And 20. We have an error. This errors because we cannot call max on an empty list. So that's easily remedied. This should short circuit. So if this this part of our expression is true, then we run this regardless or without ever testing this. So this shouldn't result in a error in code. Once again, number 5, 20. Then we have another error, and that is for p and primes, non-type object is not iterable. Oh right, we don't need to set the primes value here, because it already gets set in the sieve method, and it now returns nothing, or it returns none. So we were first changing the primes to contain an actual list of primes, and then setting the return type none to override it, and this then tried to iterate over none, which is not possible. So with that out of the way, this should work. This is not the list I'm expecting. Maybe this will help. I was running this function over a tuple containing 1 and 21 instead of the range object here. So So let's see once again 20. Yes. So here are all the prime factors of 1 and 2 and 3 and 4. And note specifically that 4 has the 2 twice. Now in this case, we needed the largest prime factor in Euler Problem 3, so we could add the 1 to prevent empty lists. But really it's not really a prime factor. I think it would be wise to let it in for 1 at the time being. But we do need to alter it if len of our pf is bigger than 1, then we want to run program number 5 for numbers up to 20. Yes, so this shows the 1 if the list would otherwise be empty, and since we are kind of expecting a list to have some kind of filling, then let's leave the 1 in for now. All the prime factors of 2 are now 2, 4 has 2 2's, and that's it. So here we see all the prime factors of every number, and we can see these decimals are when the in this bit these are the leftover numbers and are not in our prime list, because I'm kind of curious, how far does the prime sieve run? How often does it run? Let's see, we can do this. If we test 20 numbers, one, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. So it doesn't actually call the sieve for every time it runs, and that's because we put in this little bit of code. This makes sure that whenever the limit is higher than whatever we tested before, then the list is built up again. There's probably some optimization to do still here, so that we don't run through every prime we've already found in a previous iteration. We're going to work that one out later. For now, there's something specific to problem number 5 I want to discuss. We earlier in our second attempt, we trimmed this list down and omitted items that had we omitted items which were already being checked for by a higher power of that number. So 16, for instance, takes away 8, which takes away 4, which takes away 2. Any number divisible by 4 is also divisible by 2, because if we look at the prime factors, any number divisible by 4 is also divisible by 2. Because if we were to divide anything by any multiple of 4 by 2, then we would simply take the prime factor 2 away from whatever set of prime factors it has. So if we look at 12, for instance, 2 times 2 is 4, times 3 is 12, so yeah, that works out. If we divide 12 by 4, it only leaves the 3. If we divide by 4 and look at its prime factors, we simply take away these. So what we're looking for in a number such as 2520, we want to divide it by 1 through 10. So we want to be able to take away whatever prime factors are in 10, and are in 9, and are in 8, and are in 7, and are in 6. And we also want to check that once we do take away everything that is in 8, that we no longer check for 4 and for 2. So basically, of every grouping of prime factors, we want to see we want to be able to take away 3 times the prime factor 2. Or, excuse me, 4 times. Then we know it's divisible by 16 and by extension also by 8, by 4 and by 2 itself. We want the prime factor 17 to be there once and 19 once. I can see 2 3s here, and that's the maximum we're going to find. So that's another way of looking at the number. 2,300,000 and what's it? We can construct it. We can look at all the prime factors, and let's build up that as our attempt number 3. Let's set up for I in range 1. 1 doesn't really count, so let's start at 2. 1 just gives us the prime factor 1, which it's also is divisible by 1, so let's ignore 1 for now, and let's run all the way up to n plus 1 again. So in case of 20 we will now check the numbers from 2 to 20. We want prime factors of this number. We also want the unique prime factors, and we can do that using the set statement. We want to keep track of whatever prime factor we have and how often is its highest count. So I want, for this, a dictionary is particularly useful. We're going to count how often a prime factor was seen. We want to count it is, and there's the count, or excuse me, there's the list which has a count. And what do we want to count? We want to count whatever came along, and then if we've already seen this prime factor, right, let's reverse this. Whichever is bigger. Now let's see if this does what we want. Let's disable this bit again. 3 with whatever n we pass in. We should now get a dictionary of all the prime factors, all the unique prime factors we see in numbers between 1 and 20, or 2 and 20, and how often it showed up. The largest value of 2 showing up should be 3, etc. If we did not make any typos. 20 should be 4 indeed. So the prime factor 2 we saw at most 4 times in a single number. The prime factor 3 we saw at most 2 times in a single number. 5, 1, 7, 1, 11, 1, 13, 17 and 19 were all also prime factors we saw So if we multiply, if we take 2 to the 4th power, if we take 3 to the 2nd power, times 5 times 7 times 11, we should get our big number. If we did this with 10, for instance, let's rerun this for 10. Two times 2 times 2 times 3 times 3 times 5 times 7 should give us 2520. So let's make that happen. Now I'm always a bit unsure about which bit, whether or not we got the key or the value from the dictionary. Yes, these are the keys. So for each key that we find in the dictionary, the key in this case is the value that let's start our product off at 1. And then for product we already had times, and product times k to the power of how often we saw this. Let's see if this works. And let's not forget our return statement here, because previously we only printed something in this function, but we want to return it so that our main program can print this for us and time it for us. Number 5. Let's see. 10, 25, 20 seems to check out, so let's see what happens in literally no time whatsoever. Let's see what happens when we call it on 20, and that's a lot better than the 2 seconds we had earlier. So there's problem number 5, which really shows you what division does, integer division does in respect to prime factors. As a little bit of an extra, we also started to set up our very own module in which we will store all functions that are very valuable in solving Euler problems in general. We will expand this with other prime functions, such as is prime or the little set based prime factor count. We will add methods for divisibility for regular factors, and this will see a lot of extra work. So that's it, and we will see you next week. Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in O&B? Leave your thoughts in the comments. See you next time.